Hi there, this is Jiaheng, and I'm going to talk about the paper Improved Bounds for Randomly Covering Simple Hypergraphs, co-authored with Wei Mi and Heng from the University of Edinburgh. The hypergraph covering is a classical and well-studied problem in both combinatorics and computer science. We begin with the definition of a hypergraph. It consists of a vertex set, just like that for the graphs, and a set of hyperedges, each consisting several vertices. For example, this hypergraph has 14 vertices together with 5 hyperedges. A proper covering, usually omitted just as covering, forbids any monochromatic hyperedge. That is, no hyperedge shall contain only one color. For instance, this is a proper covering, even though the edge to the top has 3 red vertices. From the perspective of computer science, there are 3 or sometimes 4 different computational tasks. On an input hypergraph, the first problem is to decide if coloring exists, and the second one, which is even harder, asks us to construct one such coloring. And the last one or two require us not only to output one coloring, but also generate a uniform one and estimate the total number of proper colorings. Usually these two problems are equivalent to each other in the sense of computational tractability using self-reduction or simulated annealing. However, without any further restriction, even the deciding problem is NP-hard, implying hardness of the other problems. It's just due to a standard NP-hardness argument for 3 coloring on graphs. So, is it possible that we could design a fast algorithm for any or even all of these problems when we restrict the input to have some specific property? One such property is given by the famous about the local lemma, or abbreviated as LL if you want. The statement of LL is probabilistic, so a hyperedge being monochromatic is said to be a bad event if we just cover the vertices randomly. Usually, there is no explicit formula for the probability that we avoid all the bad events. However, the local lemma asserts that such probability is non-zero if the dependency between bad events is pretty weak. Formally, suppose each bad event happens with probability p and depends only on at most p other events, then LL says we can dodge all the bad events with a non-zero probability if p times d plus 1 is less than 1 over e. In the hypergraph covering setting, we just cover the vertices uniformly at random independently, and once the probability of avoiding all the bad events is non-zero, a proper covering exists. The probability p here depends on the number of colors and the size of each hyperedge, while the big D relies on the degree of vertices. Therefore, the parameters of interest here are the number of colors, denoted by Q, the size of each hyperedge, denoted by K if we assume all the hyperedges share the same size, which is usually called a K-uniform hypergraph, and the maximum degree. So the degree of a vertex is given by the number of hyperedges that it appears. We like delta to be the maximum degree among all the vertices. By applying LL, a covering exists if big delta is less than q to the k minus 1 over ek. We are specifically interested in the part q to the k, as this is roughly p in the LL, and we keep an eye on this term versus big delta. Okay, so for now, let's assume the LL condition. The deciding problem is trivial because we only need to output yes. The searching problem itself is easy too due to Merz-Tadisch algorithm. Note that the proof of LL by Erdős and Lovász is non-constructive and can't be used to get an algorithm. Further research shows that the LL actually gives the asymptotic threshold for computational hardness transition. The output of Merz-Tadisch algorithm is random, so it's a bit alluring to use that for the sampling problem. However, this is not true because one can show that Merz-Tadisch algorithm's output distribution is biased significantly. The hardness is essential because the approximate counting problem is NP-hard, even when the maximum degree is significantly below the LL condition. To be more specific, NP-hardness occurs when big delta is greater than q to the k over 2 for even q's, according to a recent paper co-authored with Galanis and Guo. On the other hand, we can still hope for an algorithm with local lemma type restriction. In fact, if we tighten up the condition on maximum degree to be no larger than about q to the k over 3, then there exists a sampling or approximate counting algorithm due to a recent result by Jen, Pam, and Wong. In addition, the sampler can actually be made a perfect one, a perfect Las Vegas one, due to He, Sun, and Wu. This leaves the question to decide the computational threshold for the sampling version of local lemma. This talk considers the simple hypergraphs, also known as linear hypergraphs. We call a hypergraph simple if the overlap of any pair of hyperedges is fewer than one vertex. One can easily check that the example here is simple. Applying triple L, the chromatic number of the hypergraph is delta to the 1 over k minus 1. However, for the simple case, we can shift another log delta on the base due to freeze and Mubai, and this is tied up to the constant ck depending on k. To take big delta out, this is something like k times q to the k minus 1. In the simple case, the known hardness for searching and sampling are roughly something like this, and keep an eye on the q to the k part. This is different from the q to the k over 2 for general case because the reduction depends on the overlaps being huge. For this reason, one may ask if the gap between known hardness is essential and if it's possible to design a sampler that goes beyond the cubic root of triple L. We answer them firmly. For convenience, we include a picture here to conclude the discussion of prior work. Our paper approaches q to the k over 2 from the algorithmic side, and the running time of our sampler is near linear. A natural idea is to use the so-called global dynamics. The algorithm is pretty simple. We first uniformly choose one vertex, say the one in the bottom right corner, and update its value according to its marginal distribution. In this case, no color is forbidden, and hence the marginal probability is the same for all colors. Suppose it gets updated to be red, and in the next step, suppose the red in the bottom left corner is chosen. And because coloring it to red is a red hyperedge, we can only choose between green and blue with probability half for each. One can show this Markov chain gives the correct distribution, but the problem here is how long do we need to wait for the chain to converge, or using the common terminology, does this chain mix rapidly? In practice, a Markov chain multi-color algorithm does not always succeed. Consider the solution space where the chain moves on. If it's well connected, then the chain mixes rapidly. But if the connectivity is poor, such that there is a bottleneck separating the solution space equally, then it may take a lot of time for the chain to move from one side to the other, and hence the mixing time is pretty bad. An even worse scenario is that the chain does not mix at all if the solution space is disconnected. Unfortunately, for hypergraph coloring problem in the local lemma region, we fall into the last dystopia. But if thinking one step further, sometimes this is not bad. For example, if there is a large component, then starting from a random configuration, it's highly likely that we are now inside or near the giant component. Essentially, this idea gets used by Fries and Anastos to derive a fast sampler for simple hypergraphs in some condition. Note that the second half here corresponds to the triple L, while the first half requires a number of colors to depend on the number of vertices. This is to ensure that such a giant component rises. Could we get rid of such dependency despite the disconnectivity issue? The idea introduced by Feng, Guo, Yin, and Zhang is to do Markov chain projection. For example, here we get a disconnected solution space that the Markov chain does not move from one component to another. If we project the solution space in some way, then the projected space is connected and there's a chance for the projected chain to succeed. However, what's the problem here if we further project to even smaller and well-connected space, say just two states? Even though the chain mixes super fast in this case, the cost of implementing the chain also blows up, so that's the last step where we want to recover sample from the projected distribution. There's a trade-off in between. The framework of this algorithm is pretty simple. We just run the global dynamics on the projected chain for long enough to obtain a projected sample y, and then sample proper coloring conditioning on the projection being y. According to prior discussion, we need to take care of stuff hidden behind the framework. First, we have to choose a proper projection, and then secondly, ensure the projected chain to mix rapidly, and finally, implement the chain transition efficiently. One of the main goals of the projection is to overcome disconnectivity. The hard constraints of colorings prevents us move from one to another just using global dynamics. The trick here is to bucket the colors, and the project chain only cares about the buckets instead of the colors. Under some condition, the constraint is now solved and all the bucket configurations are allowed, though the probability of each of them still differs. With the projection in hand, we can move on to the analysis of mixing time and the implementation efficiency. The q to the k over 3 barrier comes from the trade-off between these two parts, and it turns out that we need to improve both to reach 2 to the k over 2 on simple hypergraphs. Due to time limit, we only focus on the implementation part in this talk. Now suppose we've got a configuration of the buckets, and we are about to update the vertex on the top left corner. How can we know the correct projected distribution? The idea is to invert the projection on all the vertex independently, with the vertex of interest to take arbitrary color. Now, in this example, the vertex gets green, and we project again to get the new bucket for this vertex while keeping the others unchanged. So, what if the inversion is illegal? I mean, the draw coloring is not proper. We can actually repeat the last step again. This is just rejection sampling. Then the running time of each implementation depends on the expected number of rejections and samplings. Assume q and k to be constants. Each hyperedge will fail with constant probability, which means we expect exponentially so many rounds. To overcome this, note that hyperedges satisfied by the buckets affect nothing, because having different buckets implies having different colors. Therefore, we remove such hyperedges. This leaves the original graph a union of independent connected components. Only the one containing the vertex to be updated affects the marginal of that vertex, and thus we remove the remaining components too. The implementation will then be efficient if the number of hyperedges in the component is log n with high probability. How can we prove that? Usually, we do a union bound over all the possible components. However, what's the probability that a size alpha component appears or fails? By size, I mean the number of hyperedges. This is hard to answer because hyperedges may overlap each other. However, if we only use the independent hyperedges, then we can get a good upper bound. Formally, let's work on the line graph of the hypergraph. Each vertex in the line graph is a hyperedge in the original graph, and the two vertices share an edge if their original hyperedges overlap. Along introduces the so-called tree. Informally, it's just an independent set of a graph that forms a connected graph if we add edges to all the distance 2 vertex pairs. For example, the green vertex forms a tree because it's an independent set and forms a connected component on the power graph. The tree is useful in our setting because it gives a set of independent independent hyperedges in the original graph as many as possible, such that we could get a nice upper bound on the probability. It's not hard to show that any size alpha component has a size alpha over k delta to tree, so we can perform a union bound over all the two trees instead. Is a tree enough for us to reach the desired bound? Let's do a rough calculation. Assume we bucket colors into square root so many buckets, and we want the probability of existence of a big tree to be low. This in fact gets satisfied if the probability of size L to tree is less than something like inverse 2 to the L. By doing a union bound, it's just the number of two trees of size L times the probability of one certain size L to tree surviving. The last term is roughly this quantity. The L part is from the independence, while the first part is the probability of having the same buckets in a hyperedge. This, in general, is not correct, but not far from local uniformity given triple L. To bound the number of two trees, we just apply a classical counting argument, and after cleaning stuff up, it's only q to the k over 4. The q to the k over 3 is obtained by changing the bucket size to 2q to the 2 over 3 and trading off with mixing, with 3 being tied using such kind of analysis. Only considering independent hyperedges is a big waste, so we try to utilize the property of small overlaps and introduce a two-block tree. Each single vertex in a two-tree is now a size theta component or block. The example here is a two-block tree of size 3, with each block being size 3. The probability of each block is then given by this quantity. Because only the overlapped vertices sacrifice, which is at most theta squared. The technical challenge here is to derive the number of two-block trees. What we finally get is this quantity, and note that the exponent on big D, which contains big delta, is now theta plus 1 instead of 2. The theta here then cancels with the extra theta for the probability of each block, allowing us to approach k over 2. To conclude the talk, I'll provide some potential directions. The open problem is to establish the computational threshold for sampling hypergraph colorings and many other local lemma type problems. One possible approach is to overcome the connectivity issue by other methods, like updating a bunch of vertices instead of just one in each step. And another thing is that I'd like to mention is a recent recursive sampling algorithm by Arnard and Jerem. It's being used in some other very recent sampling algorithms under the local lemma setting. Can we somehow exploit that to get a better condition for hypergraph colorings? And finally, as suggested by this work, overlap information may play some part in the computational transition. In fact, when the overlap is huge, the partial rejection sampling algorithm by Guo, Jerem, and Liu can be utilized at delta equals q to the k over 2, essentially where NP hardness occurs beyond. Is it possible to incorporate PRI somewhere? In this picture, we conjecture the white ones to be trackable. That's all for this talk. Thank you for your attention and listening.